Hello, everyone. We're going to start solving this paper, which is 0620. Hopefully, you can see the screen. It's 0620, October, November 2019. So let me just quickly check whether the stream is visible. Uh, now, 0620, paper 4, theory extended. That's a chemistry paper. And let's start with the first question, which is about the periodic table. So you need to have a periodic table with you. It's about the periodic table, and they're asking refer only to elements with atomic numbers 1 to 36 in the periodic table, provided when answering the question. So 1 to 36, if I have a periodic table in front of me, let me quickly rotate this as well. This is my periodic table. 1 to 36, so which means that we are only talking about elements up to krypton. This one over here. So that's what we're talking about. Let's go back and have a look. Use information has atoms with exactly 9 protons. So go to your periodic table. 9 protons, that's the atomic number. We're talking about 9 protons is going to be fluorine over here. So we're going to write fluorine. Then it says the next part is it has atoms with 0 neutrons. That is hydrogen actually, because if you look at the periodic table, hydrogen is over here. It's right over here. If you can see my pointer, it's 1 1. The number of neutrons is the atomic mass minus the atomic number, so it's 1 minus 1, which would give you 0. So that one is hydrogen, has atoms with exactly 23 electrons. Now, protons and electrons are usually the same. So the number of protons and the number of electrons are the same for a neutral atom. So they are talking about an atom. So 23 protons. Look for an atom with 23 protons. Remember, the periodic table is arranged according to the proton number. So 23 is this one. It's over here. It's vanadium. That has 23 protons. The smaller, this lower number, the key is given, is the proton number. So this one is vanadium. The next one is has atoms with electronic structure 286. So I'll just add up the electrons. If I add up the electrons, it's going to be 10 plus it's 16 electrons in total, which means that if it's an atom, it's going to have exactly 16 protons as well. So what I need to go for is I need to look for an atom that has 16 protons. So open your periodic table again, 16 protons. It's over here. It's this one over here. Sulfur. Sulfur has a total of 16 protons. So this one is sulfur. The next one is forms ions with a charge of 3 minus containing 18 electrons. So if it has a charge of 3 minus, that indicates that it has gained 3 electrons. So in reality, it's not going to be having 18 electrons. It's going to be having 15 electrons. I mean, the iron has 18 electrons. The iron actually has 18 electrons. The atom must be having 15 electrons, which is why it's getting a 3 minus charge. That means it has gained 3 extra electrons. So I'm going to remove those 3 extra electrons. It's going to have 15 electrons. So I'm going to look for an atom that has 15 electrons. And for an atom, the electrons and protons are usually the same. So it's going to be 15 protons as well. So look for an atom with 15 protons. Go back, have a look. This over here, you can see phosphorus as the one that's having 15 protons. So let's write phosphorus over there. The next one is has a relative atomic mass that shows that it has 2 isotopes. Now, just a brief description on the relative atomic mass. Just a brief idea of what relative atomic mass is. The relative atomic mass is not just the proton number. It's basically it's not the protons plus the neutrons. It's basically the average mass of an atom. So it's the average mass of an atom uh, compared to the carbon 12th isotope. So compared to carbon 12 isotope. Now, Now, what do you mean by the average mass? The problem with the atoms is that not all atoms are the same. They have isotopes. And isotopes can have different masses. Why? Because they can have different neutron numbers. For example, there's chlorine. Chlorine could be 17 and 35. Or you could have another chlorine and it could be 17 and 37 as well. So chlorine has two isotopes. So a lot of elements have multiple isotopes. So when you take the average mass, what you mean is when you take the average mass compared to the abundance as well, when you take the average mass of the atom, the average mass somewhere comes between the two. It's not going to be 35, it's not going to be 37. If you take a sample of chlorine, it's going to be some chlorine 37 atoms, some chlorine 35 atoms. So the average mass, if you take the average mass, it's going to be in decimals, somewhere between 35 and 37. So if you look at the periodic table and you go over here at chlorine, you would notice that chlorine is uh, the mass of chlorine actually is 35.5, which means an average has been taken and chlorine has different masses. And because some chlorine atoms have different neutrons, which is why they have different masses. And when you average them, it comes to be around 35.5. So that's the answer to this question. Remember, when you're talking about the relative atomic mass, that's the average mass of different isotopes of the same element. So chlorine clearly shows that it has isotopes because its average mass is coming out. It's not a whole number, it's coming in decimals. The next part is state which metal in the first 30, which state which metal in the first 36 elements in the group 1 element which react most vigorously with water. So first 36 elements, and we talk about a group 1 metal. Now reactivity always increases down the group. So 36, remember the first 36 elements. So we'll we can't go to rubidium, that's 37. We have to stick with potassium. Potassium, the lowest in the reactivity in the group, is the one that's more reactive. So it's going to be potassium. That is the one that's going to be the most reactive element in this case, and it's going to react very very vigorously with water. The next one is reacts with air to form lime. Now remember what lime is. Lime is calcium oxide, or if there's more water, it's going to be calcium hydroxide. This one is slaked lime, that is without water. With water, it's calcium hydroxide. Now reacts with air to form lime, so it's obviously calcium. But calcium would react with oxygen to produce calcium oxide, and if there's moisture, it might result in the formation of calcium hydroxide. The next part is, so you have to remember this part, that what is lime and what is limestone as well. Limestone is also frequently used. That's calcium carbonate. That's a word that you're going to frequently witness in your exams. Moving to part C, one element in the first 36 element is used as the fuel in a fuel cell. Name this element. So one element in the first 36, now fuel cells, uh, and we're supposed to name this element. Now we have a hydrogen oxygen fuel cell. So if you remember the hydrogen oxygen fuel cell, that's a very common fuel cell. It's used in rockets, etc., etc. So hydrogen oxygen fuel cell. So it could either be oxygen over here, or you can write hydrogen over here. Both would be correct. Write the overall chemical reaction for the reaction which occurs when the element in C1 reacts in a fuel cell. So I'm just going to quickly or briefly describe what a fuel cell does. Uh, what a fuel cell would do is that it's going to have two. Okay, so it's going to have. Let me draw the fuel cell first. So there's going to be two gas jars, and gases would be entering these compartments. One side there would be oxygen gas, the other side there would be hydrogen gas coming in. And there's going to be a platinum catalyst in the middle. So a platinum catalyst would be added. So let's assume that this rod over here is the platinum catalyst. So the green one is the platinum catalyst. That's added. That catalyzes the reaction, speeds up the whole process. Now the reaction that happens on this side is oxygen reacting with two water molecules, gains 4 electrons, and ends up forming 4 OH ions. So this is the reaction that actually goes on at this electrode. Oxygen comes in, reacts, and ends up forming 4 OH ions. So a gain of electron, a reaction happens where reduction happens. Reduction means there's a gain of electron happening at one side. So if there's a gain of electron happening over here, this side would become electron deficient, because who's going to gain all the electrons? Oxygen is going to take up all the electrons. So the platinum electrode would be short of electrons. It will have a positive charge because oxygen is going to gain all those electrons. On the other side, another reaction happens where hydrogen comes in, reacts with OH ions, and ends up losing electrons. So there's another reaction that happens on this side where oxidation happens, and electrons are lost. So this side is producing electrons. Now, when it comes to fuel cells, you just have to remember these reactions that are happening in the hydrogen oxygen fuel cell. One side there's a reaction that's happening where electrons are being gained, and on the other side, a reaction is happening where electrons are being lost. And if you connect the two together, and let's say you put a bulb in between, the bulb is going to light up, because one side the electrons being produced, because the reaction that's happening over here, lots of electrons are being produced. You can see over here the reaction happens and it produces electrons. The other side, electrons are being gained, so that means that side would become electron deficient. It would get more and more positively charged, because the platinum electrode would be losing electrons, and losing electrons to oxygen gas. Oxygen gas would be the one that would be gaining those electrons. So this side would become electron deficient. It would become positively charged. So if you connect the two electrodes together, electrons would flow towards the positive side from the negative side. So this end over here is your positive terminal. This end over here is your negative terminal of the battery. Like in a cell, in a normal battery, there's a positive and there's a negative terminal. So electrons would flow, and there's going to be current, or you can say electricity is produced. So you had to write any one of the reactions. So write the so you could have talked about hydrogen and you could have written this reaction. You could have talked about oxygen and you could have written this reaction. So this is your hydrogen oxygen fuel cell. So we've gone through. I've given a brief description of what that is. Let's move to the next part of the question. The gases AR, CO2, N2O2 are in clean, dry air. Are gases commonly found in polluted air. So they're all pollutants. What percentage of clean, dry air is nitrogen? Give your answer to the nearest whole number. Now, this is a fact that must be remembered. It's 78%. Name the process used to separate O2 from clean air. So that's fractional distillation. So it's fractional distillation of liquid air. Fraction distillation. Why? Because every gas molecule has a different melting and boiling point. So you can separate them. If you can liquefy air at very low temperatures, different gases would boil or change into gaseous state at different temperatures. State one major adverse effect of the pollutant SO2. Now SO2 is acid rain. It causes acid rain. So that's one very adverse effect. Acid rain has other adverse effects like buildings corrode. So your limestone buildings are going to corrode. The other things that might happen with acid rain is that water bodies become acidic, and soil becomes acidic. So that's going to destroy marine life, and it also destroys vegetation, agriculture. So acidic soils are not good for plant growth, and it also for humans it also causes skin and eye irritation. Now the next part, NO and NO2 are produced in car engines. Describe how oxides of nitrogen form in a car engine. Now, nitrogen is extremely unreactive. Oxygen is kind of reactive, but nitrogen is extremely unreactive. Now, what happens in car engines is that at very high temperatures, uh, NO2 gas and NO gas are produced. Both are produced. You can write separate equations. So in one, NO is being produced, in the other one, NO2 is being produced. You can balance those equation. Now, uh, high temperatures in the car engine, they provide the activation energy. Remember that nitrogen is extremely unreactive. Why is it unreactive? Because it has a triple bond. The N2 molecule has a triple bond. It's very hard to actually break that triple bond. Uh, so if the high temperatures in the car engine, they make it easier for the triple bond to break because the molecules would have very high kinetic energy. And if they have very high kinetic energy, that means the molecules are going to bump into each other very vigorously and the bond is going to break. So high temperatures in car engine, they provide sufficient activation energy for the reaction. The next part is many cars have catalytic converters in their exhaust systems. Like in a catalytic converter, most of the NO formed in a car engine is changed into less harmful products. Identify these products and state the metal catalyst used. Now, the catalyst that's used is platinum or palladium. So it's a platinum or palladium. It's a honeycomb structure where gases pass through. Carbon monoxide is changed into carbon dioxide. So that's less harmful. We breathe out carbon dioxide, so it's not very harmful. Although it is harmful in the sense that it's a greenhouse gas. It causes global warming. But it's less harmful compared to carbon monoxide because it causes choking and is a poisonous gas. Nitrogen monoxide is also a poisonous gas. The actual reaction that actually takes place is this one, that carbon monoxide and NO, they both react with each other in the presence of the catalyst. Carbon monoxide gets oxidized and NO gets reduced. It loses its oxygen. And we can balance this. Now it looks, right now it looks like a balanced equation. Part F states that carbon monoxide is formed from the incomplete combustion of fossil fuels such as methane. Write a chemical equation to show the incomplete combustion of methane. So methane is burning. Methane is meth. Meth means one carbon atom, and there would be four hydrogens. It's an alkane. The general formula of alkanes is CnH2n plus 2. So you can put 1 over there. Meth is 1, and 2 into 1 plus 2 is going to give you 4. So it's methane. I'm going to react it with oxygen, and it's incomplete combustion, so it's going to produce carbon monoxide and a water molecule. Now, if it's incomplete combustion, I need to balance this equation. So it's one carbon monoxide, and they're going to be two water molecules. So that's a total of two oxygens over here, one oxygen over here. So that's a total of three oxygens. So I'm going to put 3 over 2 over here. So that would give me three oxygens. 1.5 molecules of O2 would have three oxygens. Let's move to the next part of the question, which is that it's about a carbon cycle. So you have a carbon cycle going, and the scheme shows a simple representation of part of the carbon cycle. So you're given, uh, so what's provided is, just hold on 1 minute. Okay, so Provided is the scheme shows a simple representation of the carbon cycle. So the carbon dioxide, so it's a carbon cycle, simple glucose, that's C6H12O6. Carbon dioxide getting converted into glucose. What is that process? I'm just going to solve most of the question over here. It's photosynthesis. That is the process. I can write an equation over here as well. So it's carbon dioxide, 6 carbon dioxide molecules reacting with 6 water molecules to produce C6H12O6 plus 6 oxygen molecules. This is the reaction that it's a photochemical reaction. It needs sunlight. Chlorophyll is the one that actually absorbs sunlight. So it's a photochemical reaction, photosynthesis. What's happening over here? Animals, so this over here is respiration. It's the opposite, exact opposite of that a glucose molecule is converted into energy. So C6H12O6 is oxidized by oxygen in the cells, and it ends up producing 6 carbon dioxide molecules and 6 water molecules. So that is what's going on. State the scientific terms for each process A and B. So we've already done that. One is respiration, the other one is photosynthesis. Now the next part is plants convert glucose into complex carbohydrates. So we're being asked to draw the structure of starch. Now starch is a complex carbohydrate, as I've already discussed. It's a polymer. What happens in starch is that a starch molecule, as they've shown above, is a diol. It has OH groups on both sides. So there's an OH group over here and an OH group over here as well. So on both sides, there's an OH group. And each molecule is exactly like that. So there's OH group on both sides. This one also has OH group on both sides, and so on. So there would be hundreds of molecules of this diol of glucose uh, that that would repeat. What happens is that the H and the OH are lost. Water molecules are produced. H and OH are lost. H is lost. OH is lost. So I'm going to rub them off. They're gone. So from the middle part, these would be gone. They would form water molecules. And what's going to be left is when H and OH are lost, what's going to be left is just an oxygen. And that oxygen would act as a link between the two. So let's put those oxygen atoms in the middle. And let's complete the links. So that single oxygen is going to form a linkage. And we can add a continuation bond over here. So that is what a starch or complex carbohydrate molecule would look like. This is something that you just need to remember, that if you have a diol, if you have a glucose molecule, and you're being asked to draw the structure of starch, it's a condensation polymer. The H and OH between the two groups or glucose molecules, they're going to be removed, and it's going to be a condensation reaction, and an oxygen would be left in between, and that would serve as a link of the chain that's going to be formed. The next part is complex carbohydrates break down to form simple sugars. State two ways that complex carbohydrates can be broken down into simple sugars. One is you can have enzymes; they can break it up into simple sugars, or you can use dilute acids plus heat. That would also break the chain into simple molecules. So enzymes in your body, they do this process, or dilute acids plus heat. Name a suitable technique for separating and identifying the individual sugars formed when complex carbohydrates are broken. Now remember, biological identification, many times chromatography is used. It's used for amino acids as well, and it's also used for identifying sugars as well. The next part is ammonia is an important chemical. Ammonia is manufactured by the Haber process. The reaction is reversible. What is the sign of a reversible reaction? That's an easy part. So how do you describe a reversible reaction? There's you draw two arrows. That's it. State the essential conditions for the manufacture of ammonia by the Haber process, starting from hydrogen and oxygen. Include a chemical equation to show the reaction which occurs. It's a 5-mark question. So the first thing is write down the equation: nitrogen reacting with hydrogen, and it's in equilibrium to produce ammonia. Then clearly, so include a chemical equation. We're done with that. Probably going to get 1 or 2 marks for that. The other part is state the essential conditions. So I'm going to do that. Essential conditions for this reaction. So the conditions are 450 degrees centigrade temperature, 200 atmosphere is the pressure that's used, and iron is used as a catalyst. So that's hopefully 1 mark each. So essential conditions, that's done. Include a chemical equation. So we're pretty much done what they're asking for. But I'm going to just add a few points because it's a 5-mark question. So I'll just be on the safe side. Uh, that one thing that happens is that the ammonia manufactured has a very low yield. So the unreacted, which basically means not a lot of ammonia is produced in the reaction. Nitrogen and hydrogen, they remain unreacted. Most of them are not able to react completely. The equilibrium is not shifted in the forward direction. So what happens is that the unreacted gases are fed back into the system, and ammonia is liquefied and removed. So ammonia is cooled, it's liquefied and removed, and removed. And unreacted gases, which are basically nitrogen and hydrogen, are fed back, or better word would be recycled. So they are recycled back into the system. Name one raw material which is a source of hydrogen used in the Haber process. One raw material. So it's that's air. You get nitrogen from it. And where do you get hydrogen from? Oil. Cracking of oil gives you hydrogen. These are your two raw materials. You also get hydrogen from water as well. So that could also be an answer. Now, ammonia as a base reacts with sulfuric acid to form the salt ammonium sulfate. What is meant by the term base? It's a proton acceptor. What's a proton? H plus one ions are called protons. Uh, so they accept, they're molecules that accept H plus one ions. Name the industrial process used to manufacture sulfuric acid. That's known as the contact process. And you're also being asked, write a chemical equation for the reaction uh, between ammonia and sulfuric acid. So it would form an ammonium salt. Ammonia plus sulfuric acid, so it's going to go and neutralize the sulfuric acid. The H is going to be replaced by ammonium. So ammonium is NH4 plus 1, so it's going to be bracket twice. SO4 is minus 2, so it's going to be NH4 twice and SO4. You need to balance this, so there should be two NH3 molecules. Let's move to the next part. See, when aqueous ammonia is added to iron 2 sulfate, a green precipitate is seen. This green precipitate turned red-brown at the surface. Name the green precipitate. Now, this green precipitate is FeOH2. This has to be remembered that when aqueous ammonia is added to iron 2 sulfate, a green precipitate, iron 2 hydroxide, is produced and suggests why the green precipitate turns red-brown at the surface. Now, this is an Fe2 plus precipitate. If you remember the salt analysis, Fe2 plus is green in color. Now, what happens after some time? FeOH2, it changes into FeOH3. So this is basically an Fe2 plus precipitate. This is an Fe3 plus precipitate. So in air, Fe2 plus gets oxidized. And it gets oxidized and ends up forming this brown precipitate, or what's the color? Red brown precipitate. This was your green precipitate. So an Fe2 plus precipitate, this is an Fe3 plus precipitate. So if you keep it in the air, eventually, like your rusting iron gets oxidized to this red brown precipitate. The next part is state what happens when an excess of aqueous ammonia is added to the green precipitate. Now, if you remember the salt analysis, uh, precipitate remains insoluble. It's an insoluble precipitate. So remember, now this is all memorization as well. You must know what the colors of your precipitates are. You must remember the salt analysis. Uh, what happens when you add NaOH? What happens when you add NH3? Not only is this important in ATPs, but it's also important in paper twos and paper ones as well, because you're going to be asked questions on this. It's a 4-mark question that is coming on this. Let's move to the next part of the question, which is ammonia reacts with oxygen, and you're being asked to calculate the volume. So you're being asked to calculate the volume of oxygen at room temperature and pressure that reacts with 4.8 dm cube of ammonia. Now, this is an easy question. You don't even have to go and calculate moles. The equation ratio is that 4 ammonia molecules, they react with 5 molecules of oxygen gas. Now, remember, for gases, the mole ratio and the volume ratio are exactly the same. So if 4 molecules, they react with 5 molecules of oxygen, that's the ratio. So the volume ratio would be exactly the same. 4.8 dm cube would react with, according to this ratio, it would react with X, and I'm going to do crisscross, and I'm going to try and figure out what that value is. It's going to come out to be, X would come out to be equal to 5 into 4.8 and divide that by 4. Now remember this part, this is a shortcut. You don't have to calculate moles. You don't have to do all the, you don't need to put all, use all those formulas of moles. Remember this when for gases, only for gases. The mole ratio, the ratio in which the moles are reacting, and the ratio in which the volume are reacting, they are exactly the same. So if 4 reacts with 5, 4.8 8 dm cube would react with in the similar ratio as well. So 5 into 4.8 divided 4. So let's use our calculator. It's going to be once again, it's 5 into 4.8 and divide that by 4, I think. So that gives me 6. So the answer to that is 6 dm cube. The next part is the chemical equation for the reaction can be represented as shown. So there's a reaction that's happening. Use the bond energies in the table to calculate the energy which occurs when 1 mole of NH3 reacts. Now he's talking about 1 mole of NH3. Uh, Now you have a lot of NH3s reacting, right? Uh, so what I'm going to do is, again, this is a slightly difficult question. What I'm going to do is, I'm going to calculate the bond energies for this specific reactions. Uh, so how many energy needed to break bonds? Now the first thing is how many bonds they need to be broken. Now if you look carefully, uh, that's 1, 2, and 3. So 3 NH bonds they need to be broken in one molecule, but there are 4 molecules, so that means multiply that by 4. So that's like 12 NH bonds that need to be broken. How many double bonds need to be broken? That's 1. In one molecule, that's 1, but you have 5 molecules, so that's you need to break oxygen double bond oxygen. You need to break a lot of them. You need to break exactly 5. So if I do that, it's going to be if I calculate the values, it's going to come out to be NH bond. That's the energy 391. So it would be 12 multiplied by 391. And this would be 5 multiplied by oxygen. Oxygen is 498. So let's do these calculations. I'm going to add them up, and I'm going to write the value over here. So it's 12 into 391. So 1 second. So it's 12 multiplied by 391. That gives me 4692. So 4692, and then it's a plus. The other one, which is 5 into 4, 498. This should be 4. 1 second. So it's 5 into 498. 5 times 4, 98. So it's 7182. So this comes out to be 7182 kilojoules, right? So it's 7182 kilojoules. But the thing is, 7182 kilojoules. But remember, he was talking about 1 mole of NH3. We're actually doing this for 4 moles of NH3. He's talking about the energy produced or consumed when 1 mole of NH3 reacts. Uh, so we're not doing it for 1 mole, we're doing it for 4 moles. So this is for 4 moles of NH3. So how much energy would be there for 1 mole of NH3? So that's simple. I'm going to divide that by 4. So I'm going to divide that by 4. So that would result in the energy for 1 mole of NH3. So 7182 divided by 4. Let's open the calculator again. 7182 and divide that by 4, and it gives me 1795.5. So it gives me 1795.5 kilojoules. And the next part, so remember, that's for 1 mole of NH3. The next part is energy released when bonds are formed. So how many bonds are formed? So if you look over here, that's 4 N double bond O that are being formed. So 4 N double bond O bonds are being formed. The other one is, in one molecule there's an OH bond and another OH bond. So in one molecule there are two OH bonds that are being formed. But you have a total of 6 molecules. So I'm going to multiply it by 6. So it's going to be actually 12 OH bonds that are being formed. So I'm going to add the energies. It's 4NO. NO is over here. It's 587. So it's 4 times 587. And then this side is 12 times OH. So 12 times 460. 12 times 464. So let's add them up. 4 into 587. Plus, it's going to be 12 times 464. So 4, 587. So this is 7916. So it's 7916. And now the thing is, it's 7916. If it's 7916, again, that's for this equation. When 4 molecules of NH3 are reacting. Now we are basically trying to find for 1 molecule. So I'm going to divide that by 4. This is for 4 NH3s reacting. So 1 would be, divide this by 4. So it's going to be 7916 divided by 4. And that gives me 1979 kilojoules. Now let me quickly pause and open the marking scheme as well. Maybe I've made some mistakes with the calculation, so just 1 second. Let me check. If the answers coming out to be are correct, then we can move forward. Now here you can see the marking scheme. I think our answers 7916, both of them are correct, except that he's not. The only difference is that he did not divide by 4 initially. Like he's doing the final part. The final answer is being divided by 4. We've actually, because he was talking about 1 mole, so I've started dividing by 4 initially because he was talking about 1 mole of NH3. So I did that over here. So I don't think they would have cut marks for that because they did it in the last step. We were doing it in our initial steps. We're not going to do it over here. Our final answer is going to come out to be the same. So I think we're using the same method. It's correct. I don't have any issues with that, and the examiner would probably not have any issues with that either. Uh, so let's go back. Both of our answers are correct, except because they never actually talked about. They never said that energy needed to break bonds. I mean, this part they're saying 1 mole of NH3. Over here, they're also saying 1 mole of NH3. So, which is why I started off calculating with 1 mole of NH3. So I did the division first, and I'm not going to do the division over here because, and one thing that we made a mistake was that the bond formation part is exothermic. So it's going to be minus 1979 or minus 7916. These values are going to be negative. They're going to be exothermic. So let's do that correction. So energy change when 1 mole of NH3 reacts, that's going to be the sum, the overall energy change. So it's going to be the bonds broken, which is 1795.5, and uh, minus the bonds formed, so it's minus 1979. One part is endo, bond broken. The other part is exo, bond formed, so that's in minus. Sum them up. So I'm going to add them up. It's 19. So it's minus 1979 and plus I need to add 1795.5, and I'm getting minus 183.5. So I'm getting minus 183.5. So let's even you can have that answer checked. That's minus 183.5 as well. Let's move to the next part, which is that many substances, so we have just reached question number 4 yet. So many substances conduct electricity. Identify all the particles responsible for the passage of electricity in. Now you must know that in graphite, electricity is conducted by delocalized electrons. And the same pretty much is also true for metals. Metals also have these delocalized electrons. Now, molten copper 2 bromide is electricity is conducted by ions. They don't have any free moving electrons. So all these structures, we can just quickly Google all those structures. Structure of graphite. Just 1 second. Let me, just for revision's sake, this over here is the structure of graphite. Ignore all the other things. Graphite carbon is bonded to 3 atoms, so it's a layered structure. Each carbon atom, these balls over here, each one of them is bonded to 3 other carbon atoms. So carbon has 4 electrons in its outer shell. So the 4th electron is kind of just roaming around the whole structure. It's conducting electricity, and it's a sheet-like structure, and the sheets have weak van der Waals forces between them, which is why it's a very slippery structure. The sheets can slide off one another. So it's a very slippery structure. Uh, so I can also Google metallic lattice. Hopefully we get a good diagram. This looks pretty decent. Now metallic bonding is metals always like to lose electrons. They always like to form positive ions. So you have these metals, all of them are forming positive ions and they're losing electrons, but where would the electrons go? Where would they end up? So all those electrons are basically just roaming around. They don't have any place. No one is gaining them. So they're just roaming around and they would be able to carry charge or transfer charge because electrons are charged particles. And the last one was electrolysis. Hopefully we can come up with a diagram of molten, let's say any compound. So in electrolysis, what happens in electrolysis is that you have these ions. They're the ones that are carrying charge, and the ions must be free moving. So you either need a molten electrolyte, molten ionic compound, or you need a substance that is in aqueous state. What happens in electrolysis is that these ions, the negative ions, go to the positive terminal of the battery, where the negative ions, they end up losing electrons. So the electrons are lost, and on the other side, the battery is sending electrons. So the positive ions go over there, and they end up gaining electrons. So that is how electron transfer or charges are flowing or moving. Electrons come over here, they're gained by these ions, and these ions, they end up losing electrons, and the electrons come back to the battery. So there's a constant flow of electrons in the circuit because of these free moving ions. Let's go back option. Look at B now. A student used the following apparatus to electrolyze concentrated aqueous sodium chloride using inert electrodes. So concentrated NaCl. So it's a funny looking diagram, but it's just concentrated aqueous NaCl. Suggests the name of a metal which could be used as the inert electrode. Remember, the only metal, not the only metal, but one of the main metals which is very inert or very unreactive, that's platinum. Then name the gas formed at the positive. Now this is proper electrolysis. This side is the cathode, negative. It's the cathode. Forget the diagram. This is cathode over here, and this positive side over here is your anode. Battery is sending electrons over here, and it's taking away, or the electrons are coming back from the other side. How many ions do you have in NaCl? You have Na plus one. So the Na plus one ion is going to be attracted to the negative side, and you have the Cl minus one, and then you also have two ions from water. One is H plus one, the other one is OH minus one. Now over here, what happens is, I'm going to do the electrolysis first. What happens over here is, based on the reactivity series, if you remember the reactivity series, I can also Google that just quickly. Let's bring in the reactivity series. This should be sufficient. So here's your reactivity series. Uh, Look at Na. Na is right at the top. Look at hydrogen, that's at the bottom over here. So Na is at the top, hydrogen is at the bottom. Uh, so in electrolysis, the rule is that the ones that are lower down in the reactivity series, they're the ones that end up gaining electrons. The unreactive ones, they end up gaining electrons. So in this case, it's going to be H plus one, and it's diatomic. So it's going to be 2H plus one, and it's going to gain two electrons to form hydrogen gas. So that is the reaction that's going to happen on this side. What happens to the other side? On the other side, there's another series that has to be remembered. And on the other side, it's Cl minus one. It's always, whenever it's concentrated, remember that's a rule. Whenever things are concentrated and there's Cl ions present, it's always going to be Cl minus one that ends up losing electrons. So Cl minus one is also diatomic. So it's going to lose electrons to form Cl2, and it's going to produce these two electrons. So that's the reaction that happens at your anode, positive anode. So you can write that down. This is going to be chlorine gas. Anyways, let's move on. Write an ionic equation for the reaction occurring at the negative electrode. We've already done that. Copy that. How, if at all, does the pH of the solution change during the electrolysis? Explain your answer. Now, how does the pH change? Look at what's going on. Initially, your solution had these ions. I've circled them. Now, H plus one is gone. Where did it go? Because it ended up forming hydrogen gas, and all the hydrogen gas got collected somewhere, or it escaped. And on this side, which ion went? Cl minus one. You lost Cl minus one. What happened to it? It changed into Cl2 gas. So what's left in the solution? It's Na and OH. So what's left is NaOH. So NaOH is formed. So what changes to the solution, if at all? What are the pH changes? Explain your answer. NaOH is formed, which is an alkali, obviously. So pH becomes alkaline, meaning that pH value increases above 7. Previously, it was NaCl, it was salt. So that was neutral, but now the pH is much greater than 7. The next part of the question is: a student used the following electrochemical cell. The reading of the voltmeter was 1.10 volts. Just pausing for 1 second.